Okay, the first example that we're going to look at is a time series here, the first file. So this is just a introductory example. We're going to look at why the time element of the data is important to consider. So suppose if we ignore that, suppose we don't care about the time values. Like we just look at these series of numbers as bunch of numbers can be sorted in any order. So which means the only option that we have is to take the data and fit a probability distribution. Now you're completely ignoring the time element. So you now start with ordering it from smallest to the largest and try to fit a probability distribution. And when you do that, click OK. And now you end up with a uniform distribution. So uniform distribution going from 0 through the maximum value is 218.55. So you're going to get a number in this range with equal probability. Okay, now that's not right, because you're now talking about any value in this range. So you can get a value very small, and that has equal probability as generating a quite large value. But when you look at the time element and see the series moving this way, you know that the future values are going to be high in this region and not anywhere in this range. So this is going to be not a very good idea, trying to use the probability distribution. So let's look at, okay, I'm going to copy the graph and insert it here. Okay, so, and we are not going to use uniform distribution. Okay. Okay, so now let's go to the data, and this time we're going to fit a time series fit. Okay, so when you do a time series fit, okay, so this is the screen that you will see, and you see that you have a time series plot, and then you have autocorrelation function and partial autocorrelation function that tell us what kind of variability there is. Is there trend in the time series or not? Is there seasonality or not? So in ACF, when you see a gradual decline in autocorrelation function, so this is the autocorrelation between the lag. Okay. So if you correlate the first value with the second value with the third value with the fourth value, then you're lagging the data by one period. On the other hand, if you pair up the first value with the third value, second value with the fourth value, and so on, then you're lagging by two. And you can lag by 3, you can lag by 4, you can lag by 5, and so on. So these are the correlations at various lags. Okay, lag 1, lag 2, lag 3, lag 4, lag 5, and so on. So over the different lags, if the autocorrelation function shows a gradual decline, then there is trend. So that is an indication of presence of trend. And also, if there is a spike in autocorrelation, okay, after you remove trend and if you run autocorrelation, and if there is a spike at the seasonality, suppose if you suspect quarterly data, then you will see spikes at 4, 8, and 12, and so on. If you suspect a monthly season, then you will see spikes at 12, 24, 36, and so on. So, well, we don't have to really get too deep into this. Now, if you just simply fit Now it gives you a warning that mean appears to be non-stationary. So you may want to try data transformations to improve stationality, right? So if you just ignore it and say, okay, I don't care, just go ahead and fit, and you see you end up with a fit like this. Okay, this is not the same as in your textbook. Textbook, I think it shows a Rima, but that doesn't matter. The point is that if you ignore the non-stationary nature of the data, then the time at risk fits a model that kind of stays stationary at this range. And then there is the bands that you see are 25th percentile to 75th percentile here, and then here, and then 5th percentile to 95th percentile over there. So you see that this is not, ignoring the stationarity is not a good idea. Okay, so let's try again. Okay, I'm going to, so let's move it here. Okay, so now go back to the same data. Now this time fit. Now you can select what kind of transformations you want to see. You can see there is a functional transformation that you can do, logarithmic transformation and square root transformation, but we won't do that kind of functional uh, uh, transformation. We can do detrending and deseasonalize. Okay, so that means you will extract out the trend and fit a trend equation for the extracted trend, and similarly you will extract out the seasonality and you fit a model for seasonality. So now let's say that we want detrend and here the trending is first order differencing, that is you subtract first value from the second, the third value from the second, and so on, and the first order differencing oftentimes will remove the trend, and you could do second order differencing also, but first order differencing is fine. And suppose if you just simply ignore seasonality and you just select only the first order detrending, right? First order differencing detrending. Or you can also say auto detect, and that will let at risk do the selection for what kind of transformation that we want to perform. So we will uncheck the functional transformation. So auto detect selects detrend with first order differencing. So let's go ahead and fit that. Now you see that the fit is pretty good. It very closely resembles the past data and projecting into the future. Okay, so let's get that copied over. Okay, so let's try one more, this time with seasonality. Okay, fit. Now we do auto detect. Now we'll uncheck the functional transformation, and you do deseasonalize, and there are again first order differencing and second order differencing and additive. So additive is what we want, and then we have to select period. So here this is a quarterly series, so you expect seasonality to be repeating every 4 periods. So we need to select 4 there and then fit. Okay. So that's the fit that we get. Copy and let's paste it here, or let's paste it side by side. Okay. So if you ignore stationary, if you ignore the fact that it is non-stationary, you end up with something like this, which is no good. Now this is only with trend, and this is with seasonality as well. It looks like these two are kind of similar, and you get the same model AR2, but the parameters are slightly different, and they give about the same kind of future projections. So you may try both and then see, compare the two, and then maybe average the two. So those are other options that we have. So so this is the basics of how to fit time series models to a time series data in at risk. And of course, we need to be able to do simulations on this, which we will see in examples that follows.